move on to the next talk, Victor.
Hello.
You have worked out your. Okay, we can hear you.
Okay, perfect. Let me share my screen.
Please.
Okay, I'm going full screen. Can you see me going through the slides?
Yes, it's moving. Okay.
Perfect. Okay, so yeah, welcome. Thank you for the invitation. Today I'm going to be telling you about a work that I did in collaboration with Adam Falkowski and Martin Gonzalez Alonso, which is extensively reported on this paper right here. For this talk, I had thought it adequate to title it AFB in the SMEFT, the LHC as a set physics laboratory. So let me first start by a non-controversial statement, I believe, for my introduction, which is that the indirect search for beyond the standard model physics requires very precise measurements and predictions and greatly benefits from the use of a general framework. So let me break this down for you. We have, for the last part of this statement, this general framework, and I believe that the most extensive model that has been used in order to do this kind of searches has been the standard model effective field theory, or SMEFT. And the reason why it has seen so much success is because the only requirement that it has is that you need to assume that there exists a large gap between the electroweak scale and the new physics scale. And apart from that, you also need to assume that the symmetries that you have present in the standard model also extends past its original scope into these unexplored environments. And apart from that, it is also extremely useful because it allows us to take advantage of the full EFT machinery in order to test many new physics models. And in our case, where we will be looking at observables that are located at the electroweak scale, it is good to know that this model is especially useful when we look at this kind of observables, these low energy observables, because the indirect effect of heavy new physics there is guaranteed. That is, unless there exists some kind of low energy degrees of freedom that are not included in the standard model and we don't know about yet. Okay, so moving on from that, I can also tell you about these precise measurements that I mentioned in my statement. And so far, I think that the experiments that have seen the greatest amount of success in doing this kind of searches have been LEP and LHC, each on their own fronts. So on one end, we have LEP, which provides very precise measurements, which leave little room for new physics at the electroweak scale. And on the other end, we have the LHC at Tevatron, which have also contributed to this, thanks to some of their measurements for observables in the W, top, and Higgs sector. However, the LHC so far has not found the same amount of success in constraining new physics contributions associated to the Z boson sector. And so, in light of this fact, my collaborators and me asked ourselves if it could be possible that the LHC could also compete with, or at least complement LEP by means of the measurements that it can provide for the Z observables. And that is precisely what we explore in this work. We explore this possibility by looking at Drell-Yan dilepton production, which at the electroweak scale could be used to improve our knowledge of the couplings of the set to a pair of fermions. Okay, so with that objective in mind, the first thing that we needed to do was to establish a solid theory framework with which to work with. And unsurprisingly, we chose the SMEFT, which we can see here in its Lagrangian form, divided in this standard model portion and these new physics contributions. And these new physics contributions are organized in an expansion of 1 over the new physics scale, which here is labeled as lambda. And as it is typically done, we truncate it at order lambda minus 2, so we consider only operators up to dimension 6. However, as you may know, dealing with this whole theory at once is pretty cumbersome because there exist thousands of contributions that one needs to take into account and needs to grapple with. And so it is convenient to find some justification in order to reduce the number of operators to consider at once and thus simplify the task of studying them. In our case, what we do is focus on Z and W pole observables, which are mainly sensitive to non-derivative interactions between electroweak bosons and fermions, and allow us to go from this huge Lagrangian to this slightly smaller expression, in which we have the standard model interactions between electroweak bosons and fermions. And coming from the new physics contributions, we have these corrections here, which are labeled as delta G's and are all over the place, and which indicate these new physics contributions. We chose to express these new physics contributions this way and not by means of an independent basis, such as the Warsaw basis, because we were interested in keeping track of which observables were sensitive to which corrections, and we thought that this was the best way to achieve precisely that. Here down below, we also have some operators that we need to take into account when studying these observables, which are the mass terms for the electroweak bosons. And here we only consider modifications to the W mass, because according to our input scheme, the Z mass comes as an input observable, and so we don't need to consider corrections to it. One thing that it should be mentioned before I move on is that here I am considering flavor general corrections. That is, I do not consider any sort of flavor scheme for any of these delta G's, and so they can be as different as they want. And I think that improves the versatility of the results that I will present in the following. So yeah, to summarize all that I have said here, basically what we are considering here is corrections to this sort of vertices that connect these pair of fermions, or whatever pair of fermions, with an electroweak boson. Okay, so before I move on, it should also be mentioned that apart from this reduction that has been achieved thanks to considering this kind of observables, there are other reasons why we can limit even further the parameter space that we need to consider. And one of the reasons for this is that these two, since we are working in a non-independent basis, these two brands of corrections, this delta G that connects the Z and the neutrinos and the W on the quarks, can be expressed in terms of some other corrections, and thus can be omitted, because we will address them through these other corrections here. Apart from that, also thanks to the fact that we are looking at these pole observables, the contributions for fermion operators are suppressed by some factors relative to those of delta G, and thus are neglected. And finally, there's also these dipole operators, which maybe should have been included in this expression here, but we omit them also because they are suppressed by the small fermion masses. So taking all of this into account and some other minor considerations, we end up with starting from these thousands of operators to just 20 parameters. And what we will do from now on is to try to constrict all of them at once, find limits for them. And the way we will do this is by building a likelihood fit, where we will try to find the best available observables and standard model prediction, and formulate some corrections for this standard model observables, which are linear in these coefficients here. Okay, so moving on to do that, what we do first is to turn to the best available pole observables, and what we find is all the observables that I list here. All of them come from big experiments such as LEP, SLC, LHC, and Tevatron, and they are most of them exceptionally precise. And we hope to use them in order to find limits for our Wilson coefficients. We do precisely that, and as you can see here, their precision matches the smallness of these limits matches the precision that I anticipated before, and we see here that we find limits that are pretty well and leave very little room for new physics presence in this observable, so in this scale, and going from per mil level, percent level limits, and that's that. However, out of these limits here, we are missing some of the 20 that I showed to you before, and namely we are missing these corrections to the couplings of the Z to the U and the Z to the D quark. And the reason why they are missing is because one linear combinations of the up and down quark vertex corrections is unconstrained. The unconstrained combination is precisely this one, and this is pretty bad because it means that we are not able to close the fit, and it means that we will need to be looking for some other observable or some other measurement that can be able to lift this blind direction. Before we move on, in order to search for which observable would be best fitted for this task, I believe it is useful to rearrange these four couplings so that we can separate the blind direction from the rest of the parameters space and get an idea of how well, in this case, LEP is suited in order to attack this kind of parameters. So what we do is perform a rotation in parameter space so that we end up with this linear combination T, which is proportional to this one here, and these X, Y, and Z parameters, which are uncorrelated and orthogonal linear combinations with respect to the information coming from the pole observables, and which we can restrict using only this LEP input. If we do that, ignoring the presence of the blind direction, we get these sort of limits, which are in line with the precision that we found here before. And this is sort of the precision that we aspire to get when moving on to lifting this blind direction. And so, which is the best observable that we should turn our sights to in order to try to leave this blind direction? Well, our thoughts instantly turned to LHC data, which is becoming increasingly more precise at exploring this sort of electroweak environments. And the reason why we thought the LHC could help us in this task was also because this blind direction has been already lifted by means of using this raw data, but it has been achieved with very modest precision, as you can see if you compare this limit to the ones here. And so we were hoping that the LHC could maybe improve upon or at least match the precision that we have here and strengthen the authority with which we lift this blind direction. And so focusing now on the LHC observables, we found that the cleanest observable for the task at hand was the so-called Drell-Yan forward-backward asymmetry, or AFB for short. And this asymmetry arises in the standard model due to parity-violating set couplings to fermions. So we have here in the partonic cross-section, we have this term here that is proportional to a knot power of the decay angle, of the cosine of the decay angle, which is defined here in this diagram. And this means that we will find an imbalance between the events that go in the forward direction and in the backward direction. And the reason why we think why this observable is exceptionally clean is because it consists of a quotient of cross sections, and that allows us to get rid of some QCD and PDF uncertainties that would otherwise arise when looking at this observable in a collider setting. Okay, so it seems perfect for what we want to do. However, there is a small problem, which is that this asymmetry cannot be directly observed at the LHC, because here we are not dealing with photons. And thus, first of all, we must modify the definition by including some parton distribution functions. But not only that, we have an even bigger problem than that, which is that by dealing with identical particles as the initial state in the collision, we lose the ability to define the decay angle. We lose this preferred direction with which one can build the asymmetry. And this is solved by experimentalists. I believe this is the standard procedure now, by defining the observable, considering the longitudinal boost of the dilepton system on an event-by-event basis. So what this means, basically, in very basic terms, is that when looking at the beam line, we look at the direction from which the biggest amount of energy comes for a given event, and we associate that direction with the direction of the quark. And if you assume that, you can restore the decay angle and define the observable without any problems. However, as you can imagine, this is not exactly the same as what we do in the partonic context, and so that will introduce a distortion in the hadronic incarnation of the observable when comparing it to the partonic expression. This gets summarized here, where we have here this partonic cross-section being modified by a global factor, which is a function of PDFs, but also we have here these so-called dilution factors, which is due to this consideration that I told you before. And from this expression, we can easily define the AFB observable by means of this quotient of cross sections. Okay, so now that this issue is settled, it also should be noted that the functional dependence on this observable depends on two kinematic variables, which are the dilepton rapidity, the dilepton system rapidity, and the center of mass energy, this S tilde. And this would be extremely useful for us because the fact that we have two kinematic variables that our observable depends on increases the number of independent observables at our disposal. And so our hope would be that this alone would serve us to constrain this 4-parameter space of these delta G couplings to vertex correlation to the light quarks at once with independence from light. And so with that in mind, we finally get to choose our measurement in order to try to constrain the couplings. And our measurement of choice is one of the angular coefficient A4, which is trivially related to the AFB. And the reason why we chose this is because of the availability of a fully developed standard model prediction, which turned out to be pretty difficult to find, but this was the best that we ended up with. And as we see here in this table, we have 4 independent observables, which are evaluated at the set mass beam at the pole. So we only consider one beam of this kinematic variable, but we consider 4 beams of the dilepton rapidity here. And so we repeat the same procedure as before. We formulate the likelihood fit, including this correction, which can be trivially introduced into the standard model prediction for the asymmetry. And so we move on to find restrictions for them. First, we check how good this observable is at attacking different directions in the parameter space. And unfortunately, as you can see here in these linear combinations, they are more or less all the same, which means that the LHC on its own is unable to constrain this 4-parameter space. We will need necessarily to combine these limits with LEP in order to check whether or not we are able to lift this blind direction. If still we try to restrict the parameter space using only this LHC observable, what we find for this uncorrelated and orthonormal linear combination is that the limits are almost all of them pretty bad. We see here that this X prime linear combination is basically unconstrained, and the same can be said for Y prime, and to a lesser extent Z prime. But if you look at this T prime linear combination, we find that we are surprisingly capable of obtaining per mil level constraints for these specific linear combinations. And this was unexpected because given the current precision of the LHC, this was very surprising to us. And so we had high hopes that this kind of precision would be able to go on when combining these limits with the ones coming from LEP. And so we would be able to lift the blind direction with a great deal of authority. However, unfortunately, this is also not the case, because when combining the limits coming from LEP with the limits coming from LHC, yes, we are capable of lifting the blind direction, but we are not as restrictive as we were when looking at T prime. And the reason for this is that the two directions T and T prime are mostly orthogonal, as you can see here. However, the constraining power of the LHC can still be seen here if we look at this correlation element between the Y and the T variables. And so we have achieved our result. And now what we need to do is to compare with what was achieved using this zero information. And as we see here in the marginalized 1 sigma regions, we see that in this case, when considering not only these 4 variables, but also the other 16 that I showed you before, we find that D0 is marginally better than the LHC at constraining the parameter space. However, when considering more simple scenarios, such as these individualized limits, where we consider that only these Z and T are non-zero, we find that the LHC is substantially better at constraining this parameter space. And this will also be seen in some other sorts of simple scenarios. However, all in all, we find that the LHC on its own cannot, we find no reason to discard either LHC or D0 in favor of the other. And so we thought that the best decision in order to provide the best limits was to consider all these 2 hadron collider inputs in the same fit, as well as the traditional pole observers, the left fit. And in doing so, we find these limits for these X, Y, Z, and T variables, which, as you can see, are substantially better than the ones that we found here. And we also list here these the nominal delta G's, which I remind you are these X, Y, Z, and T are linear combinations of. And we find that for the most part, we reach similar levels of precision to what we found before for the other corrections. And yeah, we are also considering here, and throughout everything that I've said so far, we are considering also the 16 parameters that were shown a couple of slides ago. However, since in this case, the introduction of LHC or D0 doesn't affect all the other coefficients, we do not list them here, as they are basically the same. And yeah, moving on to what I said before about the simple scenarios, it should also be mentioned that our observable, the AFB, provides crucial information in simple physics X scenarios. So in this case, where we only consider these corrections to up quark vertices, we find that the LEP on its own and the LEP on its own cannot, the LHC on its own and the LEP on its own cannot provide very high constraining power. When we include the LHC, the constraining power the ability that we have to constrain the parameter space is much higher, even when compared to the D0. And this gives us high hopes for the capability that the LHC may have in constraining these regions of parameter space in this electroweak environment. And finally, a comment for the nonlinear contributions. As I said before, when formulating our likelihoods fit, we didn't consider higher order correction. We considered that the EFT corrections entered only linearly. And this can be disputed and critiqued. And in the case of the left fit and the LHC fit, that is indeed the case. As we see here, the regions that come out from considering either the linear regime or the nonlinear regime are drastically different. However, when combining the two inputs, we find that the SO is much different. We find that the linear limits and the nonlinear limits are very close. They are still a little bit different, but still it's much better than what we have here. Okay, let me skip this. And with that, I reach the conclusion for my talk. As a brief summary, I have discussed the impact of LHC Z-fold measurements on constraining the Wilson coefficients of dimension 6 operators in the SMEFT, mainly vertex corrections. Well, we also had this W mass correction. Our main result is that the flight direction along the T variable is indeed lifted with the AFB atlas input. And we find that the atlas AFB information provides a significant improvement on LEP-only bounds on the ZQQ vertex corrections, even in simple scenarios with very few free parameters. And finally, some outlooks for the future. For the experimentalists in the room, we believe that in light of our results, current and future measurements of Drell-Yan dielectron production by LHC could be analyzed following a similar procedure to ours in order to extend the impact of hadron colliders in the electroweak precision program. And from the theory side, as a possible extension to our work, we believe that information from Drell-Yan cross-sections and off-pole data could be added to our fit in order to get a more general fit to both vertex corrections and for-framing operators. And with that, I am done. Thank you very much.
Thank you very much, Victor, for the interesting study and for keeping on time. There's a question from Jiayin.
Hi, thanks. It's a very interesting talk. So suppose if I look at 2B final states instead of dilepton, is it any possible to like constrain the ZBB bar coupling at LHC using your method, or is it too difficult?
Well, you're asking about B quarks, right?
Right. Yeah. I mean, there was. I'm not. Go ahead.
Yeah, we were at the LHC. The main problem that we encountered concerning B quarks is that the PDFs for the B quarks, at least if we try to include the B quarks in our study, the main issue is that the PDFs that correspond to those quarks in the proton are very small. And so when including them, as well as, well, if you include the strains, the charm or the big quark in the fit, the effect coming from the LHC is completely negligible. We're only sensitive to this light quark and the.
But can you look at BB bar final states? I mean, instead of dilepton, or is that also very difficult?
Well, I think that at the scale we're at, this is look into it at all, but I believe that this should be looked at a different scale from the electroweak, which is the one that we're considering.
Asked you for 1 minute. Could you? Oh, we lost.
If you're talking, I can't hear anything. Okay.
We can hear you now, I think.
Maybe you could try switching off your camera. Maybe it could help.
Okay. Okay, yeah, sure. Okay, do you hear me now properly? Hello?
Yeah, I think we can hear you.
Okay. Okay, so did you hear my answer to your question?
No, sorry, we lost you for like a minute. So yeah, about using BB bar as the final states of yeah. Could you repeat it?
Yeah. What I said before is that I believe that at the electroweak scale, and precisely at the pole as we were working in, I believe that we are very non-sensitive to those kind of corrections. So that's why we didn't consider them in our fit.
Okay, thanks.
Sorry, I'm Martin here. Can you hear me?
Yes, please.
Yeah, so concerning this question, so I think the question was about the final state, right? Considering a different final state, BB bar in the final state. So we didn't look at that process in particular. So of course, it could be done, the analysis of that data in a very similar philosophy. Now, I think it's a bit less promising because the data is probably less precise than in dilepton, because of course leptons are easier to detect. And also because the BB bar coupling, the constraints that we have from lab that Victor showed at the beginning of his talk are quite strong, so are at the per mil level. Then the competition is more complicated. So it will be tougher for the LHC to provide competitive bounds, but of course it should be done to have a clear answer.
Yeah, thanks for the answer. I mean, I was wondering because there was an anomaly in the lab results. So whether, I mean, if it's possible for the LHC to, I mean, get another different another check on this.
Right. No, it's indeed very, very interesting. I think it's challenging because of the anomalies is small and the size of the anomalies is small, but it's certainly interesting.
Thanks.
So we are a bit tight in time, in particular if you want the Austin CFD seminar to start on time. So I propose to leave the other questions to the Slack channel. And Victor, thank you again. Let's move on to the next talk.
Okay, thank you.
Matthew?
Yes, I'm here. Can you hear me?